In this ACT video, we're going to take a look at rules for exponents. We're also going to review simplifying radicals. So before we get started on the rules for exponents, let's make sure we understand the pieces of exponents. Right here we see the quantity 4 squared, which is 16, no problem. But let's make sure when I talk about specific pieces, you understand which piece I'm talking about. In this case, the 2 is our exponent. The 4, the big number, is the base. And 4 squared, the entire expression, is a power. Now, when we talk about radicals in a little bit, those pieces have specific names as well. So let's just say 4 squared is 16. That makes 16 a perfect square. And the 16 that's underneath the radical sign is called the radicand. And then, of course, the house looking thing is called our radical. And this is a square root, so you don't see the 2 there, but that number that goes there is called the index. So for instance, a better example to show index might be like the cube root of 8. 3 is the index. All right, so now you know the terminology. Let's go ahead and look at our rules for exponents. Just a refresher on these. First of all, anything to the 0 power is equal to 1. That works for letters like x to the 0 is equal to 1. And also works for numbers. Say we have 7 to the 0, that's equal to 1. Also, anything to the power of 1 is itself. So maybe we have x to the first, and that's just equal to x. Or maybe have 4 to the first power, that's just equal to 4. Now, some rules that you use when you're multiplying expressions in algebra, say you're multiplying and the bases are the same, then you need to add the exponents. For example, if we have x to the second times x to the fifth, that would give us x to the seventh. Same thing works for numbers. Maybe we have 3 to the third times 3 to the fifth. Well, the bases are the same here. Our bases aren't x this time. Our bases are 3. So we keep the base and we add the exponents. 3 plus 5, and that gives us 8. When you're dividing and the bases are the same, you subtract the exponents. So let's use the base x. We have x to the sixth divided by x to the second. Those bases are the same. They're both x. So we subtract 6 minus 2, top minus bottom, and that gives us x to the fourth. And likewise, it works for numbers as well. So say we have 5 to the fifth power divided by 5 to the fourth power, that would be 5 to the first power, or just 5, because 5 minus 4 is 1. And lastly, when we want to deal with negative exponents, we just move the term across the fraction bar. So for example, if we have x to the negative third, we would rewrite that as 1 over x to the positive third. But only the sign of the exponent changes. So for example, if I have 4x to the negative second, the exponent on the 4 is a 1, so it doesn't need to go anywhere. It has a positive exponent. But the x squared, the x to the negative second, goes to the denominator and becomes x to the second. So if you're unsure, make sure you have an exponent on each term, and that may help you understand which piece you need to move. All right, the second part of this video, we're going to take a look at simplifying some radicals. And if you don't know your perfect squares, you'll need to get a list of perfect squares. You probably already have many of them memorized. But we know, for example, not everything's a perfect square. Like the square root of 16 we discussed earlier is 4. But what about the square root of 12? Well, 12 is not a perfect square, and we don't always want a decimal answer. So what we're going to do is we're going to look for factors of 12 such that one of the factors is a perfect square. So I could break the square root of 12 up into the square root of 6 times to the square root of 2, but neither one of those are perfect squares. So that won't work. But we can split it up into the square root of 4 times the square root of 3. This works for us because the square root of 4 is a perfect square, the square root of 4 is 2, and I'm left with the square root of 3. I know this is completely simplified because my radicand 3, the only factors of it are 1 and 3. So as long as you don't have any perfect square factors left, you're done simplifying. Let's try another one. Let's take a look at the square root of 48. Well, if you're not sure where to get started, if you don't know your multiplication tables as well as maybe you should, then you want to take your number, the radicand, 48, and you want to start with 2 and list your factors. 2 goes into 48 24 times. Check to see if either one of these factors is a perfect square factor. If either one are a perfect square, then you're done. Either one of these are perfect squares, so I'm going to have to keep checking. So I tried 2. I'm going to go in numerical order so I make sure I exhaust all my options. So then I tried 3. Well, 3 goes into 48 16 times. We're good to go because 16 is a perfect square. That's what we're looking for. So we're going to break the square root of 48 up into the square root of 3 times the square root of 16. 16 is a perfect square. The square root of 16 is 4. And I just bring down the square root of 3, and we're done. So you want to take your radicand, find the biggest perfect square factor, and simplify from there.